All right. So last time we've talked about this basic notions on the master-slave architecture employed by Hadoop, and today we're going to continue talking about that in more detail. So last time we saw this scenario where our project manager Trisha manages the team of 4. And then we talked about this hypothetical scenario where Bob has gotten into a car accident and then he's not able to serve his job. And because of that, the project D was in the risk of getting into a trouble. So our Trisha, project manager, has came up with an idea of assigning a backup project for each individual so that even if one person is not able to finish the job for whatever reason, there still is somebody taking care of that project so that at the end of the day, the whole team can deliver the outcome to the client just in time. So, oops, I apologize. Click the wrong button. All right, there you go. So that very notion, we saw that it was the notion of this master-slave architecture in Hadoop. So basically, like what our Trisha did, a master node is going to manage the slave node. Slave nodes are the actual workers, and the master node is a computer that handles the projects, that manages the projects. So what master node does is to keep what is called the metadata, which is basically a ledger or a record of which project is assigned to which person or which slave node is taking care of which project as a backup, those kind of things. We also compared the Hadoop databases with SQL databases. So the most prominent thing was this schema on read versus schema on write. So schema on write means, so schema means a structure required by a database, and schema on write means we're going to enforce the data to have certain structure at the time of writing, at the time when the data is added to the database. So you need to, first of all, sort all the vegetables, right, into their corresponding bins before to add that to the database. So that was the schema on write, and that was the strategy that's employed by SQL versus in case of Hadoop, the strategy is schema on read. And then what that means is, well, at the time of writing, we're not going to be caring about the structuring of the information. So all data is going to be basically welcome. Okay, we're not going to do any gatekeeping. Whichever data you have, we're going to just let you dump the data. So it's basically like a gigantic salad bowl. Okay, and you don't need to really sort anything out. You just pour all the veggies into the bowl. And later on, when we query certain information, we're going to process and start to develop a structure. So that's what I mean by schema on read. So that was the most prominent distinction between Hadoop and SQL. We also talk about this a strategy to store the data. Again, in case of SQL, we have pretty strict rule. So all the information is going to be structured by column names, right? And then in case there are multiple databases, their relations had to be specified. So that is the logical way of organizing things in SQL versus in Hadoop, we don't really care. We just compress the files and then just distribute it across the database. So that was basically the strategy that is taken by Hadoop. Now, we also saw the scenario where if somebody puts in a query, so if the user queries something, then the SQL is going to perform what is called a relational search, which basically means it's going to search for the query based on the relational structure that's predefined by the time of creation of the database. Whereas in case of Hadoop, as the user enters the search query, then it's going to create a code, a computer code that can be executed by slave node servers, and then it's basically going to send out the query code to those across those slave nodes, so that the slave nodes can execute the query and then process data and then return the result. And then the last thing we talked about last time was this thing, the distinction between Hadoop and SQL, in a sense that in case of SQL, there's this thing called the two-phase commit. So not only at the time of data entry, we also make sure that the SQL query returns consistent result. And what that means is if, for example, one of the servers goes down and the server was not able to return the result, SQL is going to wait for that server to respond. Okay, and in case the server does not respond, then the SQL query is going to spit out a result that says there was an error. Okay. In case of Hadoop, again, we don't really care. We don't really care about the consistency. What the Hadoop is going to do is to basically distribute the search query across different data slave nodes, and then let the slave nodes to execute the command and then spit out the result. And then, Hadoop is basically display whatever is currently available, which means even if one server goes down, it will not bother to wait for that server. It's just going to spit out whatever is immediately available. Okay. So the reasoning behind this, and I emphasize it again, was because in case of Hadoop, we're talking about a large database. And what that means is it's really hard to enforce consistency, integrity, those kind of things to our database, right? Because we have simply too many things that we have to gatekeep. So instead of taking the reliability and consistency, the philosophy of Hadoop is, well, let's not worry too much about all the little minor details. Let's just allow the users to dump all the information to the database without gatekeeping, and later on, when the search query comes in, we should be able to handle all the schema and all this variations and things like that. So that's kind of the fundamental difference in philosophy between Hadoop and the traditional SQL databases. It seems like I received a question in a chat window, and for some reason I'm not able to see. Oh yeah, there you go. So the question is, if Hadoop has a schema on read architecture, does that mean that the client or user needs to specify what are the types of the record to be returned from the query? That's a good question. And my answer is yes. So, well, yes and no. So yes, in a sense that the actual input to MapReduce or Hadoop, HDFS is going to be the query code that contains all this information about the data type and those kind of things. But then the reason why I said yes and no is because from the standpoint of the user, you don't really need to specify all that, because And that's the beauty of Hadoop ecosystem. So from the user's perspective, you don't really need to worry too much about it, because on the surface, at the interface level, it looks pretty much similar to SQL. I mean, let me be a little more accurate about it. So there are many technology, including Spark, that allows you to interact with the Hadoop database as if you're interacting with SQL. So what it does, what those technology do is to first of all let the user to type in some SQL commands or to type in some API codes that looks pretty similar to SQL. And then internally, the technologies are going to translate that SQL-like command into something compatible to Hadoop. Okay, so at the end of the day, what goes into MapReduce or what goes into HDFS is, quite different from SQL, and you need to specify the schema. For example, when you query some information, but at the user level, you don't really worry about those things. Does my explanation make sense? So the reason why we're studying this is not to, give you some additional headache or anything, but here I basically explain some fundamental, theoretical concept. But at the end of the day, we're going to have all good news. We're going to be all just happy. And then, everything is going to be pretty much like SQL. And in fact, next week, we're going to have a chance to actually do something, okay, hands-on. So I think by that time, things will become much more clear. That was a great question. All right, so let's dive into HDFS. So HDFS, again, it stands for Hadoop Distributed File System. And what the HDFS does is essentially the same. So this is another version of that Trisha diagram, right? So, excuse me. Like I briefly mentioned, a few slides ago, sorry. So here's the schematic diagram of HDFS. And the basic principle here is when a data comes in, what HDFS does is to chop it down to individual blocks. Okay, so no matter how big your data is, what Hadoop is going to do is to split that file into smaller chunks. So by default, Hadoop uses 128 megabytes as a block size. So let's say you have 1 gigabyte of data. What it is going to do is it is going to break it down to multiple pieces of 128 megabyte, chunks, okay, which is represented as Lego blocks. And what Hadoop is then going to do is to store that across distributed storage. So in this diagram, we have 5 slave nodes, okay? Those are, by the way, called the data node in Hadoop language. So data node basically receives blocks, okay? And then like I explained earlier, what happens is for the fault tolerance, it replicates the same information multiple times. And in Hadoop, the default replication factor is 3, which means the same block is going to be replicated 3 times. So as you can see in this diagram, we have the orange block distributed over 3 data nodes. Okay, so those are the identical copies of those of the orange block. Similarly, we have the red block In case of red block, we have over here, here, and here. So we have total 3. In case of the blue block, again, we have here, here, and here. So they are replicated multiple times and then distributed over, distributed across data nodes. Okay, so that's what's happening in Hadoop distributed file system. Again, this is what happens under the hood, and from the user's perspective, you don't actually, break down the file into smaller blocks and then assign them and distribute them across the server, right? You're not going to do that on your own. It's all taken care by Hadoop. So from the surface, from the user's perspective, it looks just like any other cloud storage system. Okay, for example, I guess many of you are using Dropbox, for example, right? So when you log on to Dropbox, then you basically see the list of folders, list of files. You go into a folder, and there are subfolders and files in that folder, and so on and so forth. So you can use it pretty much like your local computer. Okay, so from the interface, Hadoop is exactly like that. From the user's perspective, you just upload the file and then forget about it. And then behind the scene, under the hood, Hadoop is basically going to chop that down into smaller chunks and then distribute them. And then when the user wants to access the file, then we're going to take a look at this. But there's the thing called the name node, and the name node contains all the information of where the blocks are located. So the name node is basically Trisha. Okay, and based on the metadata that the name node has, it's going to retrieve all the blocks and then assemble them and then spit it out to the user. And again, from the user's perspective, there's nothing so special. There's nothing to worry about. It's just like an ordinary file system. So that's really the beauty of Hadoop, because even though there's so many complicated things going on, at the end of the day, from the user's perspective, it's pretty much similar to the ordinary file system that they see every day. Okay. Now, on the side notes, I want to mention a few things because I think this is something that a lot of people would be curious about. So one possible scenario is that, let's say you have a data, but your data is only, say, 3 megabytes. What happens in this case? So in this case, the 3 megabyte of data is going to become a block of its own. Okay. So in case you have lots of those small 3 megabyte files, then Hadoop is going to create lots of blocks, okay, all of which has around 3 megabytes in size. And well, without talking, too much technical stuff, at the end of the day, this is going to be the burden imposed to Hadoop system, because you have so many blocks. Hadoop is originally intended for storing large files, and that's why they're introducing this concept of blocks. But in case you have small but multiple files, then a better practice is probably to zip all of them together and then create a larger chunk, and then distribute it, break it down to smaller blocks, and then distribute it across the server. Again, this is not something to worry too much about from the user's perspective, because there are technologies out there that does that kind of efficient management of the file. But conceptually, that's what happens in case you have a file size that is smaller than the default block size. So In case you're more on computer engineering, computer science side, then this is a useful information that you may want to know, because as a computer engineer, what you want to do is perhaps to set up a HDFS system from the scratch, and then you are the ones who will be responsible for configuring the block size and the replication factor and those kind of things, right? And when you do that, it is crucial for you to understand your client's uh, potential application. Are they going to use HDFS for a problem where they have large files, or are they going to use it for, say, I don't know, computer vision problem, for example, where each individual file is only a few megabytes, but then they have millions of JPEG images, or things like that, right? So then, depending on the application, you probably want to configure the block size and optimize it so that the files can be chopped down into a reasonable size, right? And that's how you can maximize the performance of the Hadoop system. But again, the scope of this course is not too much towards those, technical stuff in terms of how to set up HDFS and how to optimize it, but it's more on the actual analytics side. So our focus is more on the machine learning and statistical analysis. So we're not going to talk too much about those technical details. All right, so while I was explaining those, there were two questions. The first question says, how come there is a default on the blocks, and what does that mean to say question mark? Well, I don't know if I understood that question very well, but the reason why we have the blocks is because it is easier to manage, right? So let's say you have a file that is, I don't know, 16 gigabytes. Okay. If you have a file that is 16 gigabytes, then, one file becomes a gigantic chunk. And then in terms of distributed processing, it is not going to be very resilient, because each time you want to access this file, you're going to need to, process all 16 gigabytes, right? So instead, what's more beneficial is to break it down to smaller pieces. And then those smaller pieces are going to be distributed across the system. So let's say you have a 16 gigabytes of Excel sheet, okay? And then you want to retrieve and let's say the Excel sheet contains the information of the products. Okay, so you're running an online shopping mall, and then we have a 16 gigabytes of product inventory record. Now the user puts in a query. Let's say the user says, I want to take a look at the product that are ranged between $30 and $50. So I want to pull all the list of the products that are between $30 to $50 price range, right? So then what's going to happen is, the 16 gigabyte of Excel sheet is basically going to be broken down into smaller chunks, right? And then when the user puts in a query, what Hadoop will do is to distribute that query to the corresponding data nodes. And each of the data node is basically going to search for the query within the scope that is defined by the block. So block 1, for example, may contain, rows 1 to, let's say, 1,000, and then block 2 contains rows 1,001 to 2,000, and so on and so forth, right? So then in the sense of distributed search, right? Each of the nodes are responsible for searching just 1,000 rows, which is not that many compared to the original 16 gigabytes of data, right? So that's basically why the concept of block exists. And then the reason why we're setting the default block size is that, well, this is basically the maximum block size that Hadoop is going to allow, right? So if the block size is set to 128, then the 16 gigabyte piece is going to be broken down into, you know, multiple 128 megabyte pieces, right? Of course, you can configure this into a higher number, so you can set it to 512 megabytes, or you can make it smaller, so you can set it to 32 megabytes. That's totally fine. It depends on the application that you're interested in, and but no matter what, basically a larger, you know, files larger than the block size are going to be broken down into smaller blocks of that size. And that's how you can accelerate the process, and, you know, you can make the file system more efficient. So that's what the blocks are for. And the default value is the value that comes with Hadoop installation. So if you don't do anything, if you don't customize anything, the default setting is going to be 128 megabytes. All right, the second question here I have is, okay, also it relates to the 3V in big data in volume on the big data for holding the size 2, right? I don't know if I understood the question correctly. Well, if you can clarify that a little further on the chat window, I'll appreciate that. But I don't think I understood your question. It relates to volume on big data, obviously, right? Because we have a large file, so that's a volume. But it's also relevant to velocity, if you think about it. I mean, the whole point of those unstructured storage compared to SQL database, the whole point of that was to allow more efficient and resilient interaction, right? So if that was your question, that's my answer, but I'm not quite sure if I understood your question correctly. So for now, I'm going to just move on. But if you want to clarify your question, you're welcome to do so. Okay. All right. So then with those images in mind, okay, this is a little more accurate visualization of what's happening in HDFS. Okay. So we've been developing this diagram from this childish diagram explaining Trisha and her team members, and then we developed that into little and little more, you know, gradually more sophisticated diagram. And this is probably the closest to the precise description of what's going on in Hadoop. So the slave nodes, okay, those are actually called data nodes. And what data nodes does is those are the ones that stores the actual data. Okay, so data is stored in the data nodes, and then what data node does is whenever name node, which is the master node, asks for a query, it runs that query and then spit out the result and then send it over to the name node. Okay. Now, with that, what name node does is basically to manage and monitor data nodes. So the name node has the metadata, and metadata is basically a chart or ledger that says data block number 1 is in data node 2, data block number 3 is in the data node 7. You know, that kind of record is being kept in the metadata, and name node is the one that manages all that. So when the user sends a query, it goes to the name node. The name node looks up the metadata, and then send the query message, forward the query message to the corresponding data node. Okay, so if the user query concerns only the orange blocks, then it's going to send that query to the data nodes that contains only to the data nodes that contains the orange blocks. Okay, now in the meantime, in order to make it more robust, what happens here is each of the data nodes is going to send what is called a heartbeat. That's why I use this heart symbol. The data nodes are going to send the heartbeat to the name node. So that name node is aware of which data node is alive and which data node is down. Okay, so basically name node monitors data nodes through those heartbeats. Okay, and in case, well, let's say this data node is broken, so it went down, it no more sends the heartbeat, then the name node recognizes that, oh, there's some problem with this data node over here. And that is going to be reported to the user or system admin, or relevant people who are responsible for managing the cluster. So that's basically what's happening over here. Okay, so again, name node has the information about data blocks, metadata. Okay, and the metadata contains where the blocks are located, what's the size of those blocks, what is the hierarchy, which user has a permission to access that block, and so on and so forth. But it does not have the actual data. Whereas data nodes, okay, they don't know about those hierarchy, permission, or whatever. It just stores the actual data. It stores actual numbers. And then whenever there's a request from the name node, it responds to that, and then it returns the corresponding file or corresponding information, and so on and so forth. Okay. Now, what I intentionally have left out was this thing called a secondary name node. Now, the name is a little bit misleading because it sounds like a secondary name node is kind of a backup for the name node, right? It sounds like that. So a lot of people misunderstand that secondary name node exists because in case the name node goes down, we want to have a backup. Remember, in case of the data nodes, we had backups, right? So, for example, even if this node goes down, we still have the copies of the orange block, the green block, and the yellow block distributed, across the other data nodes. So even if this guy goes down, there was a backup. And because of that, a common misunderstanding is, well, isn't secondary node just a backup of the name node? And that's wrong, okay? And this is an important thing to remember. Secondary name node is not there for just a backup, okay? So in order to understand what the secondary name node does, we need to understand what the name node does for managing the metadata. Okay, so the metadata is stored in the name node in the form of what is called the FS image. Okay, an FS image is basically a gigantic log file that contains all the events that has happened from the time where the name node was created. Okay, so let's say I have booted up this system, let's say 15 days ago. The FS image basically contains all the events that has taken place over the past 15 days. So it's a gigantic file that contains all the events. Okay. Now, obviously, since this file contains a gigantic amount of data, perhaps loading this up to a RAM is going to be problematic. So the strategy that is employed by Hadoop is that instead of loading this on the RAM, we just keep it on the hard drive. And then on the RAM, we have a separate thing called an edit log. So edit log is essentially the same thing as FS image, but a smaller version of that sits on the RAM. Okay. And in order to reduce the size, so let's say the FS image is, I don't know, 5 gigabytes. Okay. That's the amount of information that's stored in the FS image. Now, the edit log is substantially smaller than that. So let's say only 32 megabytes. So in order to reduce the size of the edit log, what the HDFS does, what NameNode does, is to keep only the recent record in the edit log. So for example, again, if FS image is containing 15 days of, information, what the edit log does is it contains only, let's say, 1 hour of activities, 1 hour of transactions. Okay. So anything older than 1 hour is going to be stored in the FS image. And then anything recent than 1 hour is going to be handled by the edit log. So far, so good. So nothing too complicated so far, right? Now, what happens is, obviously, this is because of the different access speed to RAM and hard drive. Hard drives are slower to access, whereas RAM is much faster to access. So, user is going to just keep sending queries in case your Hadoop cluster is being used by thousands of people. Okay, you're working for a big company, and then there are so many users that uses the Hadoop cluster. You're going to receive lots of queries, right? And then the edit log is going to be rapidly evolve, right? And that's why we're having edit log loaded up in the RAM as opposed to the hard drive, because we need to, frequently update the edit log. Okay. Now, with that being said, what needs to happen is we need to consolidate the information in the edit log into the FS image every once in a while. Right? So this thing contains the full history over the 15 days, but it's not updated in real time. Edit log contains only 1 hour of history, but it is continuously updated in real time. Okay, so what needs to happen is, we need to consolidate that and then create a new FS image or update the FS image, right? So that consolidation process is what is called the checkpointing. Checkpointing. In the checkpointing process, what happens here is, well, it creates an updated FS image. So it's a little busy here, so let me clear all drawings. Again, this process is called checkpointing. What happens here is, let me change the color. Basically, we want to update FS image file by appending the information from the edit log. But if you think about it, if there are so many queries coming from the users, the name node is already quite busy. It's quite busy to handle, this file update request. So the task of the name node is pretty much, the bandwidth of the name node is pretty much occupied by handling, for handling the queries from the users and things like that. And the copy operation certainly takes time, right? Especially as the FS image grows, the time to consolidate the information is going to be quite significant. So the idea here is, well, instead of having the consolidation process in the primary name node, let's have another name node just for checkpointing. Okay. Now, what happens then is, okay, so now it's time to do the checkpointing. Okay. And like I said, every 1 hour, we're going to do the checkpointing. What the name node does is it talks to the secondary name node and say, hey, I think it's time for checkpointing. Can you help me doing that? And then the secondary name node says, yes, I can certainly do that. So then the secondary node retrieves the edit log, and then it mounts that edit log into the RAM of the secondary name node. And then it, in the meantime, it copies the FS image from the name node. And then, it copies that FS image into the hard drive of the secondary name node. And then the secondary name node reads this FS image and then append the information in the edit log, and then creates an updated FS image. And after that checkpointing process is done, it sends a signal back to the primary name node and say, hey, the checkpointing is done. Okay. And with that, the secondary name node is going to send the updated FS image to replace the old FS image in the hard drive of the name node. Okay. And in that way, name node can distribute the computing load to the secondary name node as far as the consolidation of the log file is concerned. Okay, so the metadata is consolidated in the secondary name node because the name node has a lot of other things to do, right? A lot of other things to handle. Now, during the time when the secondary name node, so when the checkpointing process begins, the name node actually creates, okay, let me erase all the busy drawings. So name node actually creates a temporary edit log, okay, as it gives a copy to the secondary name node. And then, whatever, so if this is the timeline and this is where the checkpointing has started, okay, and anything that comes in after this time point is going to be logged in the edit log, in the temporary edit log, okay? And then after the secondary name node replaces the old FS image, now the name node understands that there's no longer need to keep the temporary edit log. So the temporary edit log now becomes the primary, the main edit log in the name node. And that kind of a consolidation process, the checkpointing process, happens every once in a while. Okay. And then the default the time period for checkpointing is set to be 1 hour. So again, if you install Hadoop and you don't configure anything, you don't customize anything, then the checkpointing period is going to be 1 hour. Okay. Of course, this should be configured if you're a computer engineer working for this database system. The checkpointing hours has to be changed according to the application. So you're expecting, say, 5 users, only a small number of users. You're setting up a Hadoop system for a small company. A group of researchers want to have a large database. And if that's the purpose of having HDFS, then probably you don't need that much of frequent update. So the checkpointing period can be, bigger than 1 hour, versus, let's say, the HDFS is set to be to serve a large medical institution. Okay, so you're in a big metropolitan city. It's a big hospital in the middle of the downtown. And then, every day the doctors see, thousands of patients, and then, x-ray images, and, all the patient information goes in and out, and you want to use HDFS for that kind of purposes, then probably 1 hour is too long, because the edit log is going to explode pretty quickly, right? So in that case, you want to have the checkpointing period much shorter than that. Okay. All right. In the meantime, there are some questions. So the first question here is, RAM is like a cache in a computer. Yes, exactly. So cache is basically an operation of storing some critical information to a memory where you can easily access, right? So RAM is basically created to serve the purpose of caching the information. So that's exactly right. The second question, can you please repeat the role of edit log, temporary edit log? Okay. So again, temporary edit log is, like I just said, when the main edit log is being copied, and then when the FS image is being copied to the secondary name node, these informations are being transferred to the other computer, and you probably don't want to bother this edit log, right? The file is the chunk of document is being copied to in the middle of being copied to the secondary name node. But then if you happen to change the edit log, if you happen to change this document, then you're going to create a big chaos, right? So that's why the name node creates a temporary edit log, because during the time where the edit log is being copied to the other computer, you don't want to mess around with this one. Okay, so that's why we have a temporary edit log during the checkpointing. But after we have everything ready, then you don't need to keep the both primary edit log and the temporary edit log. So once the checkpointing is done, you discard the temporary edit log, and then just keep one single edit log. So that's the role of temporary edit log. Okay. All right, so that was really brief overview of Hadoop. Now we're gonna move to this technology called Spark. Okay, so Spark, if you recall that block diagram, not a block diagram, but if you recall this chart that I show you to explain the relationship between different technologies in the Hadoop ecosystem. So if you recall, HDFS was at the bottom, and then there was Yarn, the resource negotiator, and then on top of that was MapReduce. Okay, and if you recall, Spark was at the same level with MapReduce, which means Spark more or less does the same thing as MapReduce. Okay, so you can think of Spark as kind of a competitor of MapReduce. So in the documentation, it says Spark is a fast and scalable engine for large data processing and analysis. So that's pretty broad definition. So what it does in little more detail is, like I just said, it is used to replace MapReduce because it is similar to MapReduce. But in fact, Spark has way much more things to offer. Okay, which is the reason why nowadays so many people are excited about this Apache Spark technology, and a lot of companies, a lot of people has already moved to Apache Spark as opposed to MapReduce. So according to the Apache Spark website, Spark run programs up to 100 times faster than Hadoop MapReduce. in case where the processing is when the processing happens on the RAM. And still, it's 10 times faster, even if the processing happens on the disk. Okay, so I don't really know how accurate this claim is, and I don't really know how scientifically validated this claim is. But you know, but Spark is actually faster, much faster than MapReduce, because it's a new technology. It is very well optimized. It employs much easier and straightforward algorithm to handle distributed computing processes. So we're going to take a look at that. And because now Spark is such a hot technology, it started to have its own ecosystem. Well, the original Spark 1.0 had come with some, its own ecosystem. So, for example, we're gonna actually see in this in the next slide. But Spark has not only a module for mapping and reducing, it also comes with what is called a Spark SQL. Spark SQL is similar to Hive. It's something that wraps Hadoop database around the SQL language. Okay, so you can interact with the Hadoop database as if you're interacting with the traditional SQL database. So that's quite convenient tool to have, and that's included as a part of the Spark ecosystem. Spark also come with what is called an MLlib. It's a machine learning library. And it offers a lot of different machine learning algorithms that are very well optimized for distributed systems. Okay, so MLlib, in fact, is the tool that we're gonna use throughout the semester quite often. So it's one of the features of Spark that can be quite useful. And again, it's like I said, it's one of the hottest technologies. So a lot of companies actually adapt Apache Spark as their primary technology for handling big data. So Amazon, eBay, Groupon, NASA Jet Propulsion Laboratory, Yahoo, TripAdvisor, Baidu, Samsung, and many others are employing Spark as a way to manage their large database. So in fact, if you go to this URL, spark.apache.org, powered by .html. If you go to that link, you can actually see the full list of companies that uses Spark. And then you can actually see this gigantic list of companies that uses Spark, which kind of proves, how hot it is nowadays. And obviously, Spark is something that you really want to have on your resume, especially if you're looking for an industrial position. Okay, it'll be really cool technology to have on your resume. All right, so the way that Spark works is pretty much the same as the diagram that we just saw so far. So there's this thing called a Spark context, and that's the driver program, which manages all the tasks and then optimize the code for making it suitable for the Hadoop databases and so on and so forth. And in the Spark context basically sends the list of tasks to a cluster manager. And again, let me draw that diagram again. So at the bottom we had a HDFS, and then on top there was a yarn, yet another resource negotiator, and then Spark was here, right? And then MapReduce was here. And then I don't know if you recall, but right next to yarn was this thing called the Mesos. So Mesos is a resource negotiator that does basically the same thing as yarn. So Spark has an option for you. You can either use Yarn as a resource negotiator, or you can use Mesos as a resource negotiator. Or it also comes with its own resource negotiator, so that it can distribute the task and manage the task effectively throughout the Hadoop distributed file system. Okay, and in fact, Spark is not necessarily dependent on Hadoop. So there's an option for you to use something else than Yarn as a resource manager. And then instead of HDFS, you can use another type of database technology. Okay, so Spark is not dependent on Hadoop, even though it can it works pretty well with Hadoop. And that's why for the rest of the semester, I'm going to be pretty much focusing at Spark. Because if you know Spark, then you can pretty much leverage many other database technologies without having to worry about what's really happening under the hood. So as a matter of fact, what I've explained so far, right, is just for the theoretical understanding of what's really going on. But in practice, you don't really need to know any of those. You just need to know how to write a program with Spark. And then after that, you just send the Spark code to either Hadoop or some other database technology. And then, Spark will take care of everything that happens under the hood. So this can be really useful and, in fact, pretty easy to learn. Because I'm emphasizing this a lot because I'm afraid that at this point you guys are kind of scared off out of this all this complicated technology and so on and so forth. But at the end of the day, using Spark, you're going to just type some code that is pretty much similar to I don't know what are you guys familiar with? Maybe like Python pandas, for example. Pandas comes with this thing called the data frame. Spark comes with the data frame too, and they're pretty much similar in terms of syntax, the name of the functions, and things like that. MLlib in Spark is I don't know, pretty much similar to scikit-learn if you're familiar with that already. So again, in terms of learning curve, you can pretty quickly learn Spark, even if you don't feel super comfortable with all this complicated concepts of distributed computing and so on and so forth. Okay. All right. Our next slide is an overview of the quote unquote Spark ecosystem. So Spark at the core, it has all this core technology implemented in Spark, but in the meantime, Spark has its own ecosystem, like what I said. One of them is Spark SQL. Spark SQL allows you to interact with Spark as if you're interacting with a SQL database. So we're actually going to take a look at that after this class. Spark Streaming is another very useful technology that's included in the Spark ecosystem. Spark Streaming is for handling real-time data. So you're, for example, running a shopping mall, and then you're interested in processing, real-time influx of data for the recent, I don't know, 30 minutes, and then you want to quickly update your data analytics or something like that, then Spark Streaming is going to be super useful. MLlib is a machine learning library. This is something that we're going to talk a lot about throughout the semester. We are actually going to take a look at some of the features of MLlib, like linear regression. We're going to talk about K-nearest neighbor algorithm and many other machine learning algorithms. And then we're going to actually take a look at how exactly you can implement those algorithms in Spark. And at the end of the day, you will realize it's just 1 or 2 lines of the code. So it's fairly simple. Another thing I want to mention is this thing called the GraphX. GraphX is a library that sits on Spark that facilitates the analysis of graph structured data. So when I say graph here in this context, it's a graph theory graph. Okay, so you have, for example, social network data. So you have Facebook. This is you, and you have connections with your friend, and each of those individuals have some information, right? So name, age, birth date, and so on and so forth. Those are the information that's associated with each of the node. And then you want to analyze this big chunk of graph, and Spark GraphX is an excellent library for you to handle this large graph structured data set. Unfortunately, in this course, we're going to focus pretty much on these two modules, Spark SQL and Spark MLlib. And in fact, we're not going to bother too much to even talk about the Spark core, because these two are already pretty excellent interface for you, especially for beginners. So we're going to pretty much talk about MLlib and Spark SQL. We're going to touch a little bit about Spark streaming, because it's really excellent and exciting technology. GraphX, probably not, okay, because graph structured data, you not only need to understand, those programming technology, but also you need to understand the complicated mathematics behind the graph theory and things like that, which is beyond the scope of this course. So that's kind of the action plan for this semester. Now, I actually received a question from the chat, but the answer to that is in the next slide, so I'm not going to answer that. Okay, so the question was, do we mainly use Python for interacting with Spark, or do we have another language? And here's the answer. Okay, so Spark is available in Python, and this is going to be the one that we'll be using. We'll be using Python, and the reason for that is simple, because syntax is much easier, and then you don't need to compile anything. Okay, Python does not need any, code compilation. You don't need to deal with dependency. I mean, if you're familiar with C programming or Java, you're probably already familiar with what I'm talking about. Dependencies, when you have an external library, then you have to, go to the project setting and then link all the library file and the static and the DLL files and things like that. It's just a lot of hassle. Versus in Python, it's just import something, right? So it's much more simple compared to the other languages. Of course, Spark comes with two other languages. One is Java, and then the other is Scala. And Spark itself is written in Scala. So if you know Scala, actually Scala is better, because in case of Python, there is a little bit of overhead. Spark itself is written in Scala, so what Python Spark does is to wrap this Scala version of Spark around using this module called PySpark. And because of that conversion, obviously, PySpark have to, pay some, overhead, right, in terms of computational load. So if you already know Scala, then obviously Scala is a better, in my opinion, better language to use. It's more it's faster and it's more reliable. And Scala itself is not, so horrible in terms of the syntax. So it's still pretty easy to learn. But knowing that many of the courses at the University of Iowa uses Python as the primary programming language. So in this course, we're going to stick with Python. Okay? And that's it. So in this week, on Tuesday and today, we talk about the brief history of Hadoop, the yellow elephant, the toy elephant of Doug Cutting's son. That was how that was the origin of the name, and then the logo, right? And then we talk about this master-slave architecture. We talk about our project manager Trisha, right? And then how she handled multiple projects by distributing backup projects to her employees. And then, based on that, we define data nodes, name nodes, and the communication between the two. We also talk about the block structure. We divided the data into smaller blocks, and then that's basically how the Hadoop manages the file. And we also talk about the metadata, especially in the connection with the secondary name node, right? So we talk about the FS image and the edit log and how that's updated. And secondary name node, again, I emphasize, was not for backing up the primary name node. It was to help checkpointing process so that the edit log and the FS image was copied to the secondary name node, and then all of the update happens in the secondary name node, and then the updated version of FS image is sent back to the primary name node. And then in the meantime, we also compare Hadoop database versus SQL database. So Hadoop was a schema on read, whereas SQL was schema on write, right? So it's a matter of gatekeeping. So Hadoop is a little more loose and laid back structure. And then, SQL is more strict and more consistent. So, the little bit of sloppiness of Hadoop can actually be the power when you handle big data system. Obviously, if you have a database application where you need to make sure that everything follows the rule, then SQL is obviously the choice, even if you have a large data. But in many other situations, that's not really the problem. The real problem is how to make your database more resilient, more responsive, and then more flexible. So in that sense, schema on write is probably too strict, and schema on read should just be sufficient. And then lastly, we talk about Spark today, what it can do, and what Spark is essentially, and what kind of technologies are available out there. So that was the introduction module. And we have here some further reading materials. I highly encourage you to read those materials to make sure that you repeat what you learned today and last time, and then make sure that you understand the core concepts. And you'll realize I actually cited the Hadoop documentation. And I did that not because I was lazy and I didn't want to find any good reading material, but because in my opinion, Hadoop documentation is the best resource that you can learn Hadoop. That's the best, most accurate, and it's quite well written. So I really strongly recommend you to read Hadoop documentation. And in fact, throughout the semester, I'm going to point you towards Hadoop documentation quite a bit. So a lot of time, I'm just going to explain some core concepts, and then the rest of the details, I'm going to let you figure out from the Hadoop documentation. And that's going to be how this course is going to be organized throughout the semester. So that's all I have for today. And in the next lecture, we're going to actually, get our hands dirty. So far, it was basically the show that has been led by myself. But from the next time, we're going to talk about actually a little more hands-on topics. So we are actually going to use Apache Spark in Google Colaboratory. And then we're going to use Apache Spark to analyze some fun, exciting big data problem. So thank you very much, guys, and I'll see you next week.